Let's start with something small, something you can picture right now, wherever you are, lying there in the dark. Imagine a single pebble, smooth, round, sitting in your palm. Now imagine setting it down next to another pebble. 2 pebbles. That's it. That's the beginning. That's where computing starts, not with silicon chips or glowing screens or some genius in a garage, but with a person, thousands of years ago, setting one small stone next to another and using them to count. The Latin word for pebble is calculus, and that's where we get the word calculate. Every spreadsheet you've ever opened, every algorithm running quietly on your phone right now, every transaction processed by every bank on earth, all of it traces back, in some sense, to someone arranging little stones in the dirt. I think there's something beautiful about that, something grounding. So let's start there, with the stones, and we'll work our way forward, slowly, through the entire history of how humans taught machines to think. And if you fall asleep somewhere along the way, that's perfectly fine. The story will be here. Now, the need to count is ancient, really ancient. We're talking about a time before writing, before cities, before agriculture. There's a bone. It's called the Ishango bone, found near the headwaters of the Nile River in what is now the Democratic Republic of Congo. It's about 20,000 years old. It's a small piece of baboon fibula, and someone carved notches into it. Groups of notches arranged in patterns. For a long time, people debated what those notches meant. Some archaeologists thought it was just a tally stick, someone keeping track of trades or lunar cycles. But others noticed something curious. The groupings seemed to correspond to prime numbers and to a kind of doubling pattern. We can't know for sure what the person who carved it was thinking. But what we do know is that they were using a physical object to represent abstract quantities. They were offloading information from their brain onto something external. And that impulse, that desire to build a tool that helps you manage information you can't easily hold in your head, that's the thread we're going to follow all the way to the present. For thousands of years, the main computing tools were exactly what you'd expect: fingers, stones, marks on clay, knots in rope. The Inca civilization used something called quipu, these intricate systems of knotted strings, sometimes with hundreds of cords hanging from a single main cord, each knot encoding a number based on its type and position. Spanish colonizers encountered quipu in the 16th century and were baffled by them, but the Inca used them to run an empire. Tax records, census data, inventories of grain and livestock, all stored in knots. Think about that. An entire imperial bureaucracy running on string. But the tool that really dominated the ancient world, the one that lasted longest and spread farthest, was the abacus. And here's the thing about the abacus. People tend to think of it as primitive, like it's a toy. It's not. A skilled abacus operator can add, subtract, multiply, and divide with astonishing speed. There are well-documented competitions from the mid-20th century, where experienced abacus users went head-to-head against people using electric calculators, and the abacus users won. Not every time, but often enough to make the point. The abacus isn't slow. It's a different kind of fast. The earliest known abacus-like devices show up in Mesopotamia, maybe around 2700 BCE, though the dating is fuzzy. The version most people picture, beads on rods in a wooden frame, that's the Chinese swanpon, which has been in use for at least 1,000 years, probably longer. The Japanese soroban is a refined version with fewer beads per rod, optimized for speed. And the Russian shoti used horizontal wires with 10 beads each. Every major civilization, independently, arrived at some version of this idea, Represent numbers with physical objects you can slide around. It's such a natural human solution. But here's what I want you to notice. All of these tools, the tally sticks, the quipu, the abacus, they help you calculate, but they don't calculate for you. You still have to know the procedure. You still have to know that when you're multiplying, you do this sequence of steps. The tool holds the numbers, but your brain does the logic. The tool is passive. And the leap from a passive tool to an active machine, something that actually performs the steps for you, something where you set it up and it produces the answer, that leap took a surprisingly long time. Thousands of years, in fact. To understand why, you have to appreciate just how hard it is to build a reliable mechanical calculator. Think about what addition really requires mechanically. You need some way to represent digits, let's say wheels, with the numbers 0 through 9 printed around their edges. You turn the wheel to the right number. Fine. But what happens when you add 7 and 8? You get 15. The 1's digit is 5, but you need to carry a 1 into the 10's column. That carry operation, that's the killer. Because mechanically, it means that when one wheel rolls past 9 and back to 0, it has to reach over and nudge the next wheel forward by 1 position. And that nudge has to be precise. It has to happen every time, reliably, without jamming, without slipping, without the gears wearing down. And if you're carrying across multiple columns, like when you add 999 plus 1, and every single digit has to carry, then you get a cascade, a chain reaction of carries rippling across the entire machine. Building a mechanism that handles that gracefully is genuinely difficult. The first person to really crack this problem, at least in a way that's well documented, was Blaise Pascal. And his story is one of those cases where the human drama makes the engineering make more sense. Pascal was born in 1623 in Clermont-Ferrand, France. His father, Etienne, was a tax commissioner, basically a government accountant. And Etienne's job involved endless, tedious arithmetic, columns and columns of numbers, additions that had to be checked and rechecked day after day. The young Blaise watched his father grinding through this work and decided to do something about it. Now, Pascal was a prodigy, genuinely extraordinary. By the time he was 16, he had written a significant mathematical treatise on conic sections. He was the kind of mind that comes along once in a generation. And starting around 1642, when he was just 19 years old, he began designing and building a mechanical calculator. He called it the Pascaline. It used a series of interlocking gears, 6 of them in the original design, later extended to 8, each representing a decimal digit. You'd input numbers by turning small wheels on the front of the device, and the gears inside would handle the addition, including the carries. He used a clever mechanism called a sautoir, a kind of weighted powel that would accumulate energy as a digit wheel approached 9, and then release it all at once to advance the next wheel. It was elegant. It was ingenious. It was also incredibly hard to manufacture. Pascal reportedly went through about 50 prototypes. 50. The craftsmen of 17th century France were skilled, but the tolerances Pascal needed were at the very edge of what they could achieve. Each gear had to mesh perfectly with its neighbors. A tiny imperfection, a tooth slightly too thick, a shaft slightly off-center, and the whole machine would jam or give wrong answers. Pascal actually petitioned the king for a royal privilege, essentially a patent, to protect his design. He got it in 1649. But despite his efforts, the Pascaline never became a commercial success. They were too expensive, too finicky, too hard to repair. Only about 20 were ever built, and most of them ended up as curiosities for wealthy collectors. But here's what matters. Pascal proved it could be done. A machine could add numbers. Not a person using a tool. A machine doing it by itself through the interaction of its own internal parts. You set the inputs, you turned the crank, and the answer appeared. That's a conceptual leap, and once that idea was out in the world, other people started building on it. About 30 years later, in Germany, Gottfried Wilhelm Leibniz, yes, the same Leibniz who co-invented calculus, designed a more ambitious machine called the stepped reckoner. Leibniz wanted a calculator that could not only add and subtract, but also multiply and divide. His key innovation was something called the Leibniz wheel, or stepped drum. Imagine a cylinder with 9 teeth of increasing length along its surface. As the cylinder rotates, a smaller gear meshing with it will advance by a different amount depending on where. It's positioned along the cylinder's axis. Slide the small gear to one end, and it engages with 1 tooth per rotation. Slide it to the other end, and it engages with 9. This gives you a way to mechanically represent any digit from 1 to 9 and to add that digit into an accumulator with a single turn of the crank. For multiplication, you just repeat the addition, turning the crank multiple times. Leibniz built a prototype around 1694. It was beautiful in concept. In practice, it had problems. The carry mechanism was unreliable. There's that carry problem again, haunting everyone who tries this. The machine would sometimes lose a carry, or double count one. Leibniz tinkered with it for years, but never fully solved the issue. The stepped reckoner was more of a demonstration than a practical tool, but the Leibniz wheel itself, that stepped drum mechanism, turned out to be one of the most influential ideas in the history of mechanical calculation. Variations of it showed up in calculating machines for the next 250 years, and this is something worth pausing on. In the history of computing, there's a pattern you'll see again and again. Someone has a brilliant idea, builds a version that almost works, and then it takes decades, sometimes centuries, for manufacturing technology and engineering practice to catch up to the vision. The idea arrives before the world is ready to build it properly. Pascal had the right idea, but couldn't get the gears made precisely enough. Leibniz had an even bigger idea, but couldn't solve the carry cascade. The concepts were sound, the metal wasn't cooperating, so for a long time after Leibniz, mechanical calculators remained rare, expensive, and unreliable. There were various attempts. Samuel Morland in England built some interesting machines. The French inventor Thomas de Colmar eventually created the arithmometer in the 1820s, which became the first mass-produced calculator. But the really dramatic next chapter in this story doesn't come from someone trying to build a better calculator. It comes from someone trying to solve a completely different problem. Someone who wanted to build not just a machine that could calculate, but a machine that could be programmed, a machine that could follow instructions. And that someone was Charles Babbage, and his story is one of the most fascinating, frustrating, and heartbreaking tales in all of engineering history. Babbage was born in London in 1791, the son of a wealthy banker, and from an early age he was obsessed with mathematics. He was one of those children who would take apart every mechanical toy he was given, just to see how it worked inside. His father's wealth meant he had access to tutors and libraries, and by the time he arrived at Cambridge in 1810, he already knew more mathematics than most of his professors. And that's not an exaggeration. Babbage himself said it. And while he was famously not a modest man, in this case, he was probably right. Cambridge mathematics at the time was oddly behind the curve. The university was still teaching Newtonian notation for calculus, while mathematicians on the continent had moved on to the more elegant and powerful notation developed by, and here's a nice connection, Leibniz, the same Leibniz who built the stepped reckoner. Babbage and a few of his friends, including John Herschel and George Peacock, actually founded something called the Analytical Society, whose explicit goal was to promote continental mathematics in England. They were undergraduates campaigning to modernize their own university's curriculum. That tells you something about who Babbage was: brilliant, confident, impatient with tradition, and absolutely certain he was right. Now, there's a story about how Babbage first got the idea for a calculating machine, and it's one of those moments that's almost too perfect. Sometime around 1812 or 1821, the exact date is debated, and Babbage himself told the story differently at different times. He was sitting in the rooms of the Analytical Society, looking over a table of logarithms. These mathematical tables were absolutely critical to the functioning of the British Empire. Navigation, astronomy, engineering, insurance, taxation. Everything depended on printed tables of numbers that had been calculated by hand. And the problem was that these tables were full of errors, not because the mathematics was wrong, but because the calculations were done by human beings, and human beings make mistakes, especially when they're doing the same tedious arithmetic over and over, thousands of times. The people who did this work were actually called computers. That's where the word comes from originally. A computer was a person who computes, and Babbage, staring at these error-filled tables, reportedly said to Herschel something like, "I wish to God these calculations had been executed by steam, by a machine." And that offhand remark, that frustration with human error, became the obsession that would consume the rest of his life. Here's the thing about Babbage's vision. He didn't just want to build a calculator. He wanted to build a machine that could calculate mathematical tables automatically, and then, and this is crucial, print the results directly, without any human transcription step. Because he understood that errors crept in, not just during calculation, but during the process of copying results and typesetting them for printing. Every time a human hand touched the numbers, mistakes could appear. So his machine would calculate and print, end to end, with no human intervention. That's a remarkably modern way of thinking about the problem. The machine he designed to do this was called the difference engine. And to understand why it's called that, you need to know about a mathematical technique called the method of finite differences. Don't worry, it's actually quite elegant and simple once you see it. Imagine you want to calculate the values of a polynomial, say, a simple equation like x squared. The values go 0, 1, 4, 9, 16, 25, 36, and so on. Now look at the differences between consecutive values: 1, 3, 5, 7, 9, 11. See the pattern? Those differences are increasing by 2 each time. Now look at the differences of those differences. The second differences: 2, 2, 2, 2, 2. They're constant, and that's always true for a second-degree polynomial. For a cubic equation, you'd need to go to third differences to find the constant. The beautiful thing about this method is that once you've set up the initial values, generating the entire table requires nothing more than repeated addition. No multiplication, no division, no complicated operations. Just adding. And addition, as Pascal had proved 2 centuries earlier, is something a machine can do with gears. So Babbage designed a machine that could perform this method of differences automatically. You'd set the initial values on a series of columns of numbered wheels, crank the handle, and the machine would compute the next value in the table by performing a cascade of additions. Each column would add its value to the next column over, propagating through the machine, and the final column would show the result. Then you'd crank again and get the next value. And attached to the machine would be a mechanism to stamp the results into soft metal plates, ready for printing. No human copying. No transcription errors. In 1822, Babbage built a small working model, a demonstration piece with about 6 wheels that could compute tables with second-order differences. He showed it to the Royal Society, and they were impressed enough that the British government agreed to fund the construction of a full-scale difference engine. This was 1823, and the initial grant was £1,500, a substantial sum at the time. Babbage estimated the project would take about 3 years. It did not take 3 years. And this is where the story becomes both fascinating and painful. Babbage hired a brilliant engineer named Joseph Clement to actually build the machine, and Clement was genuinely one of the finest machinists in England. But the difference engine required a level of precision in its components that was essentially unprecedented. We're talking about thousands of gears, axles, and linkages that all had to mesh perfectly. Remember that pattern we talked about? The vision outrunning the manufacturing capability? Here it is again, in its most dramatic form yet. Babbage was designing a machine that needed parts made to tolerances that the machine tools of the 1820s could barely achieve. Clement had to invent new tools and techniques just to make the components. Every gear had to be cut with extraordinary accuracy, because in a machine with this many moving parts, small errors would compound and cascade, and the carries wouldn't propagate correctly. The project dragged on, and on, and on. The costs kept climbing. Babbage and Clement had a difficult relationship, disputes over money, over workshop ownership, over who owned the specialized tools that Clement had built. By 1832, they had produced a working demonstration section of the difference engine, about 1/7 of the complete machine, and it was a genuine marvel. It had about 2,000 parts. It worked beautifully, and it could calculate to 6 decimal places. You can actually still see it today at the Science Museum in London, and it's a gorgeous piece of engineering. But the full machine was never completed. By 1842, after the British government had spent over £17,000, roughly equivalent to several million in today's money, they pulled the funding. The project was abandoned. Now, you might think that would be the end of the story. A brilliant but impractical man, an overambitious project, a cautionary tale about scope creep. But here's what's wild about Babbage. The difference engine wasn't even his biggest idea. While he was still struggling to build it, he had already conceived of something far more ambitious. Something that, when you understand what it was, will genuinely take your breath away. He called it the analytical engine, and it is, without exaggeration, the conceptual ancestor of every computer you have ever used. The difference engine could compute mathematical tables using one specific method. It did one thing. The analytical engine was designed to do anything. It was a general-purpose computing machine. Babbage envisioned it with a mill, what we would now call a central processing unit, where arithmetic operations would be performed. It had a store, what we'd call memory, where numbers could be held for later use. It could perform addition, subtraction, multiplication, and division. It had conditional branching, meaning it could examine a result and decide what to do next based on whether that result met certain conditions. Think about what that means. The machine could make decisions. It could follow different paths through a calculation depending on intermediate results. That's not a calculator. That's a computer. And here's the kicker. It was designed to be programmed using punched cards. Babbage borrowed this idea from the Jacquard loom, a French weaving machine invented by Joseph Marie Jacquard around 1804. The Jacquard loom used cards with holes punched in them to control which threads were raised and lowered during weaving, allowing complex patterns to be produced automatically. Babbage saw those punched cards and realized the same principle could be used to feed instructions to a calculating machine. One set of cards would specify the operations: add this, multiply that, store this result. Another set would specify which numbers in the store to operate on. The machine would read the cards, execute the instructions, and produce results. You could change the cards, and the same machine would perform a completely different calculation. That's programmability. That's software. And this is where another remarkable figure enters the story. Augusta Ada King, Countess of Lovelace, usually known simply as Ada Lovelace. She was the daughter of the poet Lord Byron, though she never really knew her father. Her mother, Lady Byron, was terrified that Ada might inherit her father's poetic temperament and what she considered his dangerous instability. So she pushed Ada toward mathematics and science from a very young age. And Ada turned out to be extraordinarily gifted. She met Babbage at a party in 1833 when she was just 17, and she became fascinated by his machines. In 1842, an Italian mathematician named Luigi Menabrea published a paper describing the analytical engine, based on lectures Babbage had given in Turin. Ada was asked to translate the paper from French into English, and she did, but she also added her own extensive notes, which ended up being about 3 times longer than the original paper. These notes are remarkable. In them, Ada described how the analytical engine could be instructed to perform specific computations. She wrote out a detailed plan for how the machine could compute Bernoulli numbers, a complex sequence in mathematics, and this is often cited as the first computer program ever written. Whether that title is entirely fair is debated by historians, since Babbage himself had sketched out programs for the engine. But Ada's notes went further in important ways. She thought deeply about what the machine could and couldn't do. She speculated that it might one day be used to compose music or manipulate symbols beyond mere numbers. She also, presciently, cautioned that the machine could only do what it was instructed to do. It could not originate anything on its own. It had no capacity to think. That distinction between following instructions and actually understanding is one we're still wrestling with today. But here's the sad part. The analytical engine was never built, not even close. It existed only in Babbage's extraordinary detailed drawings and notes, thousands of pages of them. The engineering challenges were even more daunting than those of the difference engine. Babbage spent the rest of his life refining the designs, but he could never secure funding, and by the time he died in 1871, the machine existed only on paper. The British government had been burned once and wasn't interested in funding another grand mechanical project. Babbage died frustrated and somewhat embittered, convinced that the world hadn't understood what he was trying to do. And honestly, he was right. The world didn't understand. It would take nearly 100 years before anyone built a machine that could do what Babbage's analytical engine was designed to do. 100 years. The ideas were all there: the central processor, the memory, the stored instructions, the conditional branching, the input-output separation. All of it was there in the 1830s and 1840s, designed in brass and iron and punched cards, and then essentially forgotten. When electronic computers were finally built in the 1940s, most of the engineers involved had never heard of Babbage. They reinvented many of his concepts from scratch. Now, In the decades after Babbage, the world didn't stand still. Mechanical calculation continued to evolve, just along more modest and commercially practical lines. Remember the arithmometer, Thomas de Colmar's machine? By the second half of the 19th century, mechanical calculators were becoming genuine business tools, and there's one development from this era that deserves special attention because it connects directly to the punched card idea that Babbage borrowed from the Jacquard loom and points straight toward the 20th century. In 1890, the United States faced a crisis that was, at its heart, a data processing problem. The U.S. Constitution requires a census every 10 years, and the 1880 census had taken nearly 8 years to fully tabulate. The country was growing so fast that officials worried the 1890 census might not be finished before the 1900 census began. A young engineer at the Census Bureau named Herman Hollerith had an idea. He designed a system of punched cards, each card representing one person, and an electromechanical machine that could read those cards by pressing them against a bed of mercury-filled cups. Wherever there was a hole in the card, a pin would pass through and make contact with the mercury, completing an electrical circuit. The machine would count and sort the cards automatically, and it worked spectacularly. The 1890 census was tabulated in about a year. Hollerith's company eventually merged with several others and, in 1924, was renamed International Business Machines, IBM. And the punched card, Jacquard's invention, Babbage's inspiration, Hollerith's practical tool, would remain the primary method of feeding data into computers well into the second half of the 20th century. Think about that timeline for a moment. An idea from a French weaver in 1804, adapted by a visionary English mathematician in the 1830s, turned into a practical census tool in 1890, and still going strong in the 1960s and 70s. Some ideas just have legs. But here's the thing. Punched cards and mechanical calculators, as useful as they were, could only take you so far. They could add, subtract, sort, and tabulate. What they couldn't do, not really, was think in any flexible sense. They couldn't make decisions. They couldn't branch. They couldn't take the result of one calculation and use it to decide what to do next. At least not in the fluid, general-purpose way that Babbage had dreamed about with his analytical engine. To get there, to get to what we'd actually recognize as a computer, the world needed something beyond gears and punched holes. It needed a new theoretical foundation. And that foundation came from the most unlikely place imaginable. A quiet, awkward, brilliant young man sitting in a Cambridge study in the mid-1930s, thinking about a problem in pure mathematics that seemed to have absolutely nothing to do with machines at all. His name was Alan Turing, and the problem he was wrestling with is one of those deep, almost philosophical questions that mathematicians love. It's called the Entscheidungsproblem. That's German, and it basically asks, is there a mechanical procedure, a definite step-by-step method, that can determine whether any given mathematical statement is true or false? The great mathematician David Hilbert had posed this challenge in 1928, and it was considered one of the central open questions in the foundations of mathematics. Hilbert believed the answer was yes, that mathematics was, at its core, complete and decidable. That there existed some ultimate algorithm that could settle any mathematical question. Turing proved him wrong. In 1936, at just 24 years old, Turing published a paper called On Computable Numbers, and it's one of those rare papers that reshapes everything. But here's what's fascinating. To prove that no such universal decision procedure could exist, Turing first had to define, rigorously, what a mechanical procedure even meant. What does it mean to compute something? And to answer that, he invented an imaginary machine. Picture this: an infinitely long strip of tape divided into squares. Each square can hold a symbol, let's say a 0, a 1, or be blank. There's a head that can read one square at a time, write a symbol, erase a symbol, and move one square to the left or one square to the right. And there's a table of instructions, a set of rules that says, if you're in state A and you read a 1, write a 0, move right, and go to state B. That's it. That's the whole machine. It's absurdly simple. It sounds almost like a toy. But here's what's wild about this. Turing showed that this simple imaginary device, given the right set of instructions on its tape, could compute anything that is computable. Anything. Any calculation that any computer will ever perform, from rendering a video game, to simulating a galaxy, to running the algorithm that recommends what you should watch next on a streaming service. All of it can, in principle, be done by this little tape-reading machine, given enough time and enough tape. That is a staggering claim, and it has held up for nearly 90 years. And Turing went further. He described what he called a universal machine, a version of his imaginary device that could simulate any other Turing machine. You'd encode the instructions of the machine you wanted to simulate as data on the tape, and the universal machine would read those instructions and carry them out. Think about what that means. The machine and the program are both just patterns of symbols. The hardware and the software are, at some fundamental level, the same kind of thing. Data and instructions live in the same space. This is the idea, this precise idea, that makes your laptop, your phone, every general-purpose computer in the world possible. The concept that a single machine can run any program, that you don't need to build a new machine for every new task, that you just write new instructions, that traces straight back to Turing's 1936 paper. Now, Turing wasn't the only one to reach these conclusions. Across the Atlantic, the American mathematician Alonzo Church arrived at essentially the same result around the same time, using a different mathematical formalism called lambda calculus. The two approaches were proven equivalent, and the result, that there are well-defined limits to what can be computed, is known as the Church-Turing thesis. But it was Turing's formulation, with its vivid image of a physical machine reading and writing on a tape, that captured the imagination. It was concrete. You could almost build the thing. And eventually, people did build things very much like it. But let's not rush ahead. Let's stay with Turing for a moment, because his life is one of those stories that's both extraordinary and deeply sad, and it illuminates something important about the relationship between pure ideas and the messy, political human world in which those ideas have to survive. Turing went to Princeton after publishing his paper, worked with Church, got his PhD, and then returned to England, just as the world was falling apart. When World War II broke out in 1939, Turing was recruited to Bletchley Park, the secret British code-breaking center housed in a Victorian estate about 50 miles north of London. And this is where theory met practice in the most urgent way imaginable. The Germans were using a cipher machine called Enigma to encrypt their military communications. Enigma was an electromechanical device. It used a series of rotating wheels, or rotors, to scramble each letter of a message in a way that changed with every keystroke. The number of possible settings was astronomical, on the order of 158 million, depending on the version. The Germans believed Enigma was unbreakable. They were wrong, but proving them wrong required a combination of mathematical brilliance, engineering ingenuity, and sheer dogged persistence that is hard to overstate. Turing didn't work alone. The Polish Cipher Bureau had actually made the first crucial breakthroughs against Enigma before the war, and their work was shared with the British in 1939. But Turing took those insights and pushed them much further. He designed a machine called the Bomb-A, an electromechanical device about 6 feet tall, full of rotating drums that mimicked the action of Enigma's rotors. The bomb didn't try every possible setting. Instead, it used logical deductions to eliminate impossible configurations, narrowing the search space dramatically. It exploited the fact that Enigma had certain structural weaknesses. For instance, a letter could never be encrypted as itself, which might sound like a minor detail, but it gave the codebreakers a crucial foothold. By the middle of the war, Bletchley Park was reading a substantial portion of German encrypted communications, sometimes within hours of interception. The intelligence produced, code-named Ultra, is widely credited with shortening the war by at least 2 years and saving countless lives. And Turing was at the heart of it. But here's the thing. All of this was classified, top secret. For decades after the war, nobody knew. Turing couldn't talk about what he'd done. The world had no idea that this quiet mathematician had helped save it. After the war, Turing threw himself into the project of building actual electronic computers. He worked at the National Physical Laboratory in London, where he designed a detailed plan for a stored program computer called the ACE, the Automatic Computing Engine. The design was remarkably advanced, but bureaucratic delays and institutional friction slowed the project. Turing, impatient and frustrated, eventually moved to the University of Manchester, where another team was already making rapid progress. And this is where we need to zoom out a bit, because the late 1940s were this incredible moment when the theoretical ideas, Turing's universal machine, the concept of stored programs, were colliding with new electronic technologies, and multiple teams around the world were racing to build the first true electronic computers. It's messy and contested, and there's no single clean narrative, which is actually what makes it so interesting. Let's talk about what electronic means here, because it matters. Before electronics, computing machines were either mechanical, gears and levers, or electromechanical, like Hollerith's tabulators, which used electrical circuits to count and sort, but still relied on physical moving parts like relays. A relay is basically an electrically controlled switch. A small current in one circuit activates an electromagnet that physically moves a metal contact to open or close another circuit. Relays work, but they're slow. They can switch maybe 50 or 100 times per second, and they wear out because they have moving parts. The breakthrough was the vacuum tube. Now, a vacuum tube is a beautifully simple device in concept. You have a glass tube with the air pumped out. Inside, there's a heated filament that boils off electrons, that's called thermionic emission, and a metal plate that collects them. Put a voltage between the filament and the plate, and current flows. But add a third element, a wire grid between the filament and the plate. And now you can control the flow of electrons by varying the voltage on that grid. A small signal on the grid controls a large current between filament and plate. The tube can amplify signals, and crucially, it can act as a switch, on or off, 1 or 0, with no moving parts. And it can switch thousands of times per second, orders of magnitude faster than a relay. Vacuum tubes had been around since the early 1900s, used in radio and telecommunications, but it took a while for anyone to think of using them to build a computing machine. The first person to really pursue this was a German engineer named Konrad Zuse, working in his parents' living room in Berlin in the late 1930s. Zuse built a series of machines, the Z1, Z2, Z3, and Z4, that were remarkably sophisticated. The Z3, completed in 1941, used telephone relays rather than vacuum tubes, but it was arguably the world's first working programmable digital computer. It used binary arithmetic, zeros and ones, which was itself a radical choice at the time when most people assumed computers should work in decimal. Zuse had independently arrived at many of the same architectural ideas as Babbage, and like Babbage, he struggled for funding and recognition. The Z3 was destroyed in a bombing raid in 1943, and Zuse's work remained largely unknown outside Germany for years. Meanwhile, in the United States, a physicist named John Atanasoff at Iowa State College had built a small electronic device between 1937 and 1942 called the Atanasoff-Berry computer, or ABC. It used vacuum tubes and could solve systems of linear equations. It was special purpose, not programmable in the general sense, and it was never fully operational. But it introduced key ideas: binary arithmetic, electronic switching, regenerative memory, that would prove important. And it became the subject of a bitter legal dispute decades later, when a court ruled in 1973 that Atanasoff's work predated and influenced the machine that had long been credited as the first electronic general-purpose computer. That machine was ENIAC, the electronic numerical integrator and computer, built at the University of Pennsylvania by John Mauchly and J. Presper Eckert, and completed in late 1945. ENIAC was a monster. It filled an entire room, weighed 30 tons, used about 18,000 vacuum tubes, and consumed 150 kilowatts of power. It could perform 5,000 additions per second, which was breathtaking at the time. It was originally designed to calculate artillery firing tables for the Army, another case of war driving computation forward. But here's the interesting wrinkle about ENIAC. It wasn't a stored program computer. To reprogram it, you had to physically rewire it, plugging and unplugging cables and flipping switches. It could take days to set up a new problem. It was programmable, but painfully so. The people who did that programming, by the way, were mostly women. 6 women, specifically, who were among the first professional programmers in history. Kay McNulty, Betty Jennings, Betty Snyder, Marlyn Meltzer, Fran Billis, and Ruth Lichterman. They figured out how to make ENIAC work, how to break complex mathematical problems into sequences of operations that the machine could execute. They invented debugging techniques, developed subroutines, and did all of this with almost no documentation and no recognition at the time. Their contributions were largely overlooked for decades, which is a pattern you see again and again in the history of computing. The people who actually make the machines work, who write the code and find the bugs, getting less credit than the people whose names are on the building. Now, even as ENIAC was being built, the people involved were already thinking about how to do it better. And the key insight, the one that would define the next generation of machines, and really every computer since, came from a collaboration between the ENIAC team and a towering figure in 20th century mathematics, John von Neumann. Von Neumann was a Hungarian-born polymath who seemed to be the smartest person in every room he ever entered, and he entered a lot of rooms. He contributed to quantum mechanics, game theory, nuclear weapons design, and half a dozen other fields. When he learned about ENIAC in 1944, he immediately grasped its significance and got involved. In June 1945, von Neumann circulated a document titled first draft of a report on the EDVAC being the planned successor to ENIAC. And this document, just over 100 pages, laid out the architecture that would become the blueprint for virtually every computer built since. The key idea, and this is where Turing's theoretical work and practical engineering finally merge, was the stored program concept. Instead of rewiring the machine for each new task, you would store both the data and the instructions in the same memory. The program would be just another kind of data, sitting in memory right alongside the numbers it was crunching. The machine would fetch instructions from memory one at a time, execute them, and move to the next one. And because the program was in memory, it could modify itself. It could change its own instructions during execution, which opened up possibilities that nobody had fully imagined yet. Think about what that means for a second. A program that can look at its own instructions and rewrite them on the fly. It sounds almost alive, doesn't it? In practice, early programmers used self-modifying code for very mundane reasons. Things like adjusting memory addresses in loops, because those early machines didn't have the elegant indexing features we take for granted now. But conceptually, it was profound. It meant the boundary between program and data was dissolved. A computer wasn't just a calculator anymore. It was something genuinely new, a general-purpose machine that could, in principle, become any machine, depending on what instructions you fed it. And that's exactly what Turing had described in his 1936 paper, that universal machine idea, now made real in copper and glass. But here's the thing about the stored program concept. Knowing the idea and actually building a working machine around it are two very different challenges. And in the late 1940s, a quiet but intense race unfolded to build the first true stored program computer. Several groups were working on it simultaneously, on both sides of the Atlantic, and the story of who got there first is one of those wonderful, messy human dramas where credit is contested and feelings run deep even decades later. The group that most historians point to as first across the finish line was at the University of Manchester in England. A small team led by Frederick Williams and Tom Kilburn built a machine they called the Manchester Baby, officially the Small-Scale Experimental Machine, or SSEM. It ran its first program on June 21, 1948. The program was nothing glamorous. It was designed to find the highest proper factor of a number, and it took about 52 minutes to do what you could manage with pencil and paper in a few seconds. But that wasn't the point. The point was that the instructions lived in the same memory as the data, and the machine fetched and executed them automatically. It was a stored program computer, and it worked. Now, what made the Manchester Baby possible was a clever solution to one of the hardest practical problems in early computing: memory. You need some way to store both data and instructions, and you need it to be fast enough that the processor isn't just sitting there waiting around for the memory to catch up. The technology Williams and Kilburn used was something called the Williams tube, or Williams-Kilburn tube. And it's a beautifully weird piece of engineering. They took a standard cathode ray tube, the same kind of tube that would later be used in television sets, and figured out that when you fired an electron beam at a spot on the phosphor-coated screen, it created a tiny charge difference that you could detect. A dot on the screen could represent a 1, and the absence of a dot could represent a 0. So your memory was literally a pattern of glowing dots on a screen. You could read it back by detecting the charge, and you could write to it by firing the beam at a new position. It was ingenious, and it was also temperamental. The charges would fade, so you had to constantly refresh them, reading each bit and rewriting it before it disappeared. The tubes were sensitive to vibration. to temperature changes, to stray electrical interference. Getting them to work reliably was a constant battle. But they were fast, and they gave you random access. You could read any bit without having to sequentially scan through everything else first. That was a huge advantage over something like mercury delay line memory, which was the other main technology being explored at the time. Mercury delay lines. Let me tell you about these, because they're one of those technologies that sounds completely improbable. The idea came from wartime radar work. You take a tube filled with liquid, mercury, and you send a pulse of sound, an ultrasonic pulse, in one end. The pulse travels through the mercury at the speed of sound, which in mercury is about 1,450 meters per second. When it reaches the other end, a sensor picks it up, amplifies it, and sends it back in the other end again. So your data is literally a train of sound pulses circulating endlessly through a tube of mercury. A pulse represents a 1, a gap represents a 0, and as long as you keep the loop going, the data persists. The EDSAC, the electronic delay, storage automatic calculator, built at Cambridge under Maurice Wilkes, used mercury delay lines and ran its first program in May 1949, about 11 months after the Manchester baby. Some people argue EDSAC was the first practical stored program computer, because unlike the baby, which was really just a proof of concept, EDSAC was designed from the start to be useful, to run real programs for real researchers, and Wilkes deserves enormous credit. He was a meticulous, thoughtful engineer who also pioneered ideas about programming libraries and subroutines that would shape software development for decades. But the Manchester team got there first with the basic principle. Meanwhile, across the Atlantic, things were more complicated. Von Neumann's own machine at the Institute for Advanced Study in Princeton, usually just called the IAS machine, didn't become fully operational until 1951 or 1952, depending on how you define operational. Which is ironic, right? The man who wrote the blueprint was not the first to build from it. Part of the reason was that von Neumann was a theorist at heart, and the practical engineering challenges of building reliable hardware were not really his forte. He had brilliant engineers working with him. Julian Bigelow was the chief engineer, but the project faced constant delays, funding complications, and the kind of maddening hardware reliability problems that plagued everyone working with vacuum tubes. And this is worth pausing on, because vacuum tube reliability was the defining engineering headache of this entire era. A single vacuum tube might have a mean time between failures of thousands of hours, which sounds fine until you remember that ENIAC had 18,000 of them. If each tube has an average lifespan of, say, 2,500 hours, then statistically, you'd expect a tube to fail somewhere in the machine every few minutes. The actual failure rate wasn't quite that bad, because the engineers learned to run the tubes at lower voltages and keep them powered on constantly. Turning tubes on and off was what stressed them most. But still, a significant portion of each day was spent finding and replacing failed tubes. The ENIAC team got remarkably good at this, developing diagnostic routines and keeping careful records, but it was a constant grind. This reliability problem is actually what drove one of the most important transitions in computing history: the move from vacuum tubes to transistors. And the transistor story is one of those tales where you can see the entire future hinging on the work of a few people in a single laboratory. Bell Telephone Laboratories in Murray Hill, New Jersey. Late 1947. William Shockley, John Bardeen, and Walter Brattain. These three men would share the 1956 Nobel Prize in Physics for what they accomplished, but the human dynamics among them were complicated. Shockley was the group leader, brilliant but abrasive, the kind of person who needed to be the smartest in the room and didn't handle it well when he wasn't. Bardeen was quieter, a theorist with a deep understanding of solid-state physics. He would go on to win a second Nobel Prize, the only person ever to win 2 in physics. And Bratton was the experimentalist, the one with gifted hands who could actually build the delicate apparatus needed to test ideas. Shockley had been thinking about solid-state amplifiers since before the war. The idea that you could use a semiconductor material to do what a vacuum tube did, but smaller, cheaper, more reliable, and with no warm-up time. But his initial designs didn't work, and he couldn't figure out why. It was Bardeen who cracked the theoretical problem, developing the concept of surface states that explained why Shockley's field effect approach was failing. And then Bardeen and Bratton, working together in a burst of intense experimentation in November and December of 1947, built the first working transistor, the point contact transistor. On December 16, 1947, they demonstrated it. A tiny device made with a sliver of germanium and 2 gold contacts pressed against it, close together, that could amplify an electrical signal. Here's the thing about that moment, though. When Shockley found out that Bardeen and Bratton had succeeded, and that his name wasn't on the patent because it was their experimental breakthrough, not his, he was furious. Quietly furious, in the way that drives a certain kind of person to work even harder. He went off on his own, and within a few weeks had designed a different, better kind of transistor, the junction transistor, which was more practical, more reliable, and easier to manufacture. It was Shockley's junction transistor that would actually change the world. But the personal cost was real. Shockley's behavior grew increasingly difficult. He sidelined Bardeen and Brattain, took credit publicly in ways that minimized their contributions, and created such a toxic atmosphere that Bardeen eventually left Bell Labs entirely, going to the University of Illinois, where he would do the work on superconductivity that earned him that second Nobel. Brattain was reassigned to a different group. The team that had made one of the most important inventions of the 20th century was broken apart by ego and resentment. Now, the transistor didn't immediately transform computing. The first transistors were expensive, finicky, and not obviously better than a good vacuum tube for many applications. It took years of materials science work, figuring out how to purify germanium, and then silicon to extraordinary levels, how to manufacture transistors reliably and cheaply, how to design circuits that took advantage of their properties. The first fully transistorized computer is generally considered to be the Manchester University transistor computer, which ran its first program in November 1953. But the machine that really demonstrated what transistors could do for computing at scale was the IBM 7090, which appeared in 1959. It was roughly 6 times faster than its vacuum tube predecessor, the IBM 709, while being smaller, more reliable, and using far less power. And this is where you start to see computing shift from being a specialized scientific tool to something with much broader implications. Because transistors didn't just make computers faster, they made them reliable enough to run for days and weeks without constant maintenance, small enough to fit in a single room instead of filling an entire floor, and cheap enough that businesses could start to justify buying them. The 1950s saw the emergence of the commercial computer industry, with companies like IBM, Remington Rand, and others competing fiercely for customers in banking, insurance, manufacturing, and government. The UNIVAC one, built by Eckert and Mauchly, the same team behind ENIAC, became famous when CBS used it to predict Eisenhower's landslide victory in the 1952 presidential election. And suddenly, the public had a sense that these machines could do something remarkable. But even as transistors were transforming computing, someone was already thinking about the next leap. And this next idea, the one that would take us from rooms full of equipment to the smartphone in your pocket, came from a frustration so practical, so mundane, that it's almost funny. The problem was called the tyranny of numbers, and it was exactly what it sounds like. As circuits got more complex, as engineers wanted computers to do more and more, they needed more and more transistors, and every single one of those transistors had to be wired to every other component it needed to talk to, by hand, with actual physical wires. Imagine you've got a circuit board with 10 transistors on it. That's manageable. You solder the connections, you check your work, you move on. Now imagine 100 transistors. That's trickier, but still doable. Now imagine 10,000. Now imagine 100,000. Each one is a tiny little component that has to be placed precisely, soldered to its neighbors, connected by fine wires to the right points in the circuit. Every single solder joint is a potential point of failure. Every wire is something that could come loose, corrode, break. And the more connections you have, the more likely it is that something, somewhere, will go wrong. This was the tyranny of numbers. It wasn't a theoretical limit. It was an engineering nightmare. You could design a circuit on paper that would do extraordinary things, but actually building it, actually manufacturing it reliably, was becoming nearly impossible. The complexity of the wiring was growing faster than anyone's ability to manage it. Military systems were especially affected. The guidance computer for an intercontinental ballistic missile might need tens of thousands of components, all wired together with absolute precision, and it had to work perfectly the first time, because, well, you can't exactly pull over and debug a missile mid-flight. The failure rates were staggering. Some estimates suggested that for every component you added to a circuit, you were adding a measurable probability that the whole thing would fail, and the Department of Defense was spending enormous sums just on maintaining and replacing faulty electronic equipment. So here's the situation in the late 1950s. Transistors are wonderful. They're small, they're fast, they're efficient. But the way we're using them, as individual components wired together on circuit boards, has hit a wall. The wall isn't physics. The wall is manufacturing. The wall is human hands and solder and wire. And two people, working independently, in different companies, in different states, arrived at essentially the same solution within about 6 months of each other. Their names were Jack Kilby and Robert Noyce, and between them, they invented the integrated circuit, the single most consequential invention in the history of electronics, and arguably one of the most important inventions in human history, full stop. Let's start with Jack Kilby, because he got there first, if only barely. Kilby was a tall, quiet Kansan, 6'6", soft-spoken, the kind of guy who'd rather be working at his bench than talking at a meeting. He'd been working at a company called Centralab in Milwaukee, making circuit components, and in 1958, he took a new job at Texas Instruments in Dallas. He started in May, and here's a detail that matters. Because he was new, he hadn't accrued any vacation time. So when most of the company shut down for a 2-week mass vacation in July, Kilby was one of the few people left in the building. He had the labs essentially to himself. And he spent those 2 quiet weeks thinking about the tyranny of numbers. His insight was deceptively simple. What if, instead of making each component separately and then wiring them all together. You made everything. Transistors, resistors, capacitors, all of it. Out of the same block of semiconductor material? What if the entire circuit was one piece? No wires between components, no solder joints, just one monolithic chunk of germanium with everything built right into it. On September 12, 1958, Kilby demonstrated his first integrated circuit to his bosses at Texas Instruments. It was rough, a little sliver of germanium with gold wires sticking out of it, sitting on a glass slide. It looked almost handmade, almost fragile. But when he applied a signal, an oscillating waveform appeared on the oscilloscope screen. The circuit worked. Multiple components, one piece of semiconductor. It was a proof of concept, not a product, but it was real. Now, 6 months later, and about 1,500 miles to the west, Robert Noyce was working on the same problem at Fairchild Semiconductor in Mountain View, California. Noyce was, in almost every way, Kilby's opposite in temperament. Where Kilby was reserved and methodical, Noyce was charismatic, gregarious, the kind of person who walked into a room and everyone noticed. He'd been one of the so-called traitorous eight, a group of young physicists who'd left William Shockley's new semiconductor company in 1957 because Shockley, brilliant as he was, had become an impossible boss. Remember Shockley from the transistor story? The man who'd pushed Bardeen and Brattain aside to claim credit? Well, his management style hadn't improved. He'd become paranoid and erratic, at one point demanding that his employees take lie detector tests over a minor incident. The eight who left founded Fairchild Semiconductor, and it would become one of the most important companies in the history of technology. Noyce's version of the integrated circuit was different from Kilby's in a crucial way. Where Kilby had used individual fine wires to connect the components on his germanium chip, Noyce realized you could use a technique called the planar process, developed by his colleague Jean Hoyerny at Fairchild, to lay down thin lines of metal directly on the surface of the chip, creating the connections as part of the manufacturing process itself. No wires at all. Everything, the components and the connections between them, was built into the chip in layers using photographic masks and chemical etching. This was the version that would change the world. Noyce's approach was inherently mass-producible. You could use the same photolithographic techniques to make one chip or 1,000 chips on a single wafer of silicon. The connections were as reliable as the components themselves, because they were made the same way, and because everything was so small, the electrical signals had shorter distances to travel, which meant the circuits could operate faster. The patent dispute between Kilby and Noyce, or rather, between Texas Instruments and Fairchild Semiconductor, dragged on for years. Both men filed patents, both companies claimed priority, and the legal battle wound through the courts for nearly a decade before they eventually agreed to cross-license their technologies. In the end, history has generally given them joint credit. Kilby received the Nobel Prize in Physics in 2000. Noyce, sadly, had died in 1990 and couldn't share it, since the Nobel isn't awarded posthumously. But both men knew, and both companies knew, that the integrated circuit was an idea whose time had come. If Kilby and Noyce hadn't invented it, someone else would have, probably within a year or two. The pressure of the tyranny of numbers was just too great. And here's what happened next. And this is where the story starts to accelerate in a way that's almost dizzying. Once you could put multiple components on a single chip, the obvious question became, how many components can we fit? In 1965, a young engineer at Fairchild named Gordon Moore, another one of the traitorous eight, and later the co-founder of Intel with Noyce, wrote a paper for Electronics magazine in which he observed that the number of components on an integrated circuit had been doubling roughly every year since the invention of the chip. He predicted this trend would continue for at least another decade. He was being conservative. The trend didn't just continue for a decade, it continued for half a century. It became known as Moore's Law, and it's not really a law of physics. It's more like an observation about the pace of engineering innovation, a self-fulfilling prophecy that the semiconductor industry organized itself around. Every couple of years, the doubling time was later revised to about every 2 years. Engineers found ways to make transistors smaller, pack them more densely, and the chips got more powerful. In 1965, you could fit about 64 components on a chip. By 1971, Intel's first microprocessor, the 4004, had 2,300 transistors. By the mid-1980s, you were looking at hundreds of thousands. By the late 1990s, millions. Today, the chips in modern smartphones and computers contain billions of transistors, each one so small that you could fit thousands of them across the width of a human hair. Think about that progression for a second. From Kilby's rough little germanium slab with its gold wires, to billions of transistors on a chip the size of your fingernail in about 60 years. There's nothing else in human history that has improved at that rate. Nothing. If cars had improved at the same pace as semiconductors, a modern car would travel at the speed of light and cost about a penny. But the integrated circuit didn't just make computers smaller and faster. It made an entirely new kind of computer possible. One that would have seemed like science fiction to the engineers working on ENIAC or even the IBM 7090. Because once you could put an entire processor on a single chip, you could put a computer anywhere. In a desk, in a briefcase, eventually, in your pocket. The story of how we got from the first integrated circuits to the personal computer is one of the great dramas of the 20th century, and it involves a cast of characters so colorful, so ambitious, so brilliantly weird that you almost couldn't make them up. It starts in a stretch of apricot orchards and small towns south of San Francisco that was, in the early 1960s, just beginning to earn a new nickname. The traitorous Eight had set up Fairchild Semiconductor there. Other companies were clustering nearby, drawn by Stanford University's engineering program and by a culture that was starting to reward risk-taking and entrepreneurship in ways that the more buttoned-up East Coast electronics industry didn't quite understand. People were leaving established companies to start new ones, and the new ones were spinning off even newer ones. And the whole ecosystem was feeding on itself in this extraordinary cycle of innovation and competition. They called it Silicon Valley, after the element at the heart of everything. And one of the first things that happened there, in a modest little startup founded by Noyce and Moore in 1968, was the invention that would make the personal computer possible. Intel. The name was short for Integrated Electronics, and from the start, Noyce and Moore had a clear vision. They weren't going to build computers. They were going to build the chips that went inside computers, memory chips specifically, because in the late 1960s, computer memory was still made from tiny magnetic rings called ferrite cores, threaded by hand onto fine copper wires in these intricate grids. It was expensive, it was slow to manufacture, and Noyce and Moore knew that semiconductor memory could replace it entirely. And they were right. Intel's early memory chips were a hit. But the thing that really changed everything, the invention that cracked open the door to the personal computer, came about almost by accident. In 1969, a Japanese calculator company called Busicom approached Intel with a contract. They wanted Intel to design a set of custom chips for a new line of desktop calculators. The original plan called for something like 12 separate chips, each one designed to handle a specific function. It was a perfectly reasonable request, the kind of thing semiconductor companies did all the time. But one of Intel's engineers, a guy named Ted Hoff, looked at the design and thought it was unnecessarily complicated. Hoff had a background in computer architecture. He'd done his PhD at Stanford, and he realized that instead of building 12 specialized chips, you could build one general-purpose chip that could be programmed to do all those different tasks. Instead of hardwiring the logic for each function into silicon, you'd create a tiny processor that could follow instructions stored in memory. A computer on a chip. Think about what that means. Before Hoff's insight, every time you wanted a chip to do something new, you had to design a whole new chip. That's expensive, it's slow, and it means every product needs its own custom silicon. But a general-purpose processor? You design it once, and then you just change the software. The same chip can run a calculator, or control a traffic light, or manage an elevator, or, eventually, run a word processor, or a spreadsheet, or a web browser. The hardware becomes universal. The software becomes the thing that changes. Hoff proposed the idea, and Intel's management liked it. The detailed design work fell to a brilliant Italian physicist named Federico Faggin, who had joined Intel from Fairchild. Faggin was a perfectionist, and he drove himself relentlessly, working nights and weekends to get the chip right. The result, released in November 1971, was the Intel 4004. It was the world's first commercial single-chip microprocessor. And here's the thing, it was tiny. The die was about the size of a fingernail, and it contained those 2,300 transistors we talked about earlier. Its clock speed was 740 kilohertz, which is laughably slow by modern standards. Your phone's processor runs about 4 million times faster. But the 4004 could execute 60,000 instructions per second, and it had roughly the same computing power as ENIAC, that 30-ton room-filling monster from 1945. All of ENIAC's capability, compressed onto a sliver of silicon you could hold between your thumb and forefinger. Now, the 4004 was a 4-bit processor, meaning it could only work with 4 bits of data at a time. That's fine for a calculator, but it's pretty limiting for anything more ambitious. Intel followed it up in 1972 with the 8008, an 8-bit processor, and then in 1974 with the 8080, which was faster, more capable, and easier to program. The 8080 is really the chip that lit the fuse. It ran at 2 megahertz. It could address 64 kilobytes of memory, and it cost about $360. Not cheap, but within reach of a hobbyist. And hobbyists were exactly the people who were paying attention. Because here's the cultural context you need to understand. In the early 1970s, computers were still institutional things. They belonged to corporations, governments, universities. The idea that an individual person would own a computer was to most people in the industry somewhere between absurd and pointless. Ken Olsen, the founder of Digital Equipment Corporation, one of the most successful computer companies in the world at the time, reportedly said in 1977 that there was no reason anyone would want a computer in their home. And from his perspective, it made sense. Computers were expensive tools for processing payroll and tracking inventory and running scientific simulations. What would a regular person do with one? But there was this whole subculture, mostly in the San Francisco Bay Area, that saw things completely differently. These were people who had grown up with the counterculture of the 1960s, who believed in individual empowerment, who were deeply suspicious of centralized authority, including the centralized authority of big computer companies and the institutions they served. For them, the idea of a personal computer wasn't just a technological curiosity. It was a political statement. Putting computing power in the hands of individuals was a way of democratizing information, of breaking the monopoly that big organizations had on this incredibly powerful tool. One of the key figures in this movement was a guy named Lee Felsenstein, an engineer and activist in Berkeley who had been involved in the free speech movement. Another was Ted Nelson, who coined the term hypertext and dreamed of a universal information system decades before the World Wide Web. And then there was the Homebrew Computer Club, which started meeting in a garage in Menlo Park in March 1975. It was basically a bunch of electronics enthusiasts who got together to share ideas, swap parts, and show off what they were building. The meetings were chaotic and passionate and wildly creative, and out of that garage came an astonishing number of companies and products that would shape the entire industry. The spark that ignited the Homebrew Club, and really the entire personal computer revolution, was a machine called the Altair 8800. It appeared on the cover of Popular Electronics magazine in January 1975, and it was basically a box with a bunch of toggle switches and blinking lights on the front panel. No keyboard, no screen, no storage. You programmed it by flipping switches to enter binary code, one instruction at a time, and the output was just a pattern of lights. It was, by any practical measure, almost useless. But it was a computer, a real computer, built around the Intel 8080 processor, and it cost $397 as a kit you assembled yourself. The magazine expected to sell a few hundred. They got thousands of orders in the first month. The Altair was designed by Ed Roberts, who ran a small, struggling electronics company called Emites in Albuquerque, New Mexico. Roberts was a big, burly guy, a former Air Force officer, and he was basically betting everything on this machine. His company was deep in debt, and the Altair was a Hail Mary. It worked. The response was overwhelming. And two young guys who read that Popular Electronics cover, one at Harvard, one nearby, immediately saw the opportunity. Their names were Bill Gates and Paul Allen, and they called Roberts to tell him they'd written a version of the basic programming language for the Altair. They hadn't, actually. They hadn't even seen an Altair. But they figured they could write one before Roberts asked for a demonstration. Allen flew to Albuquerque with the software on a paper tape, loaded it into an Altair, typed print 2+2, and the machine typed back 4. It worked on the first try. That software became the first product of a little company Gates and Allen called Microsoft, later Microsoft. Meanwhile, back at the Homebrew Computer Club, a young engineer named Steve Wozniak was attending the meetings and getting inspired. Wozniak was one of those rare natural talents. He could look at a circuit design and just see how to make it simpler, more elegant, using fewer chips. He'd been obsessed with electronics since childhood, building little computers and calculators out of whatever parts he could scrounge. And after seeing the Altair, he decided he could build something better. Not just a box with switches and lights, but a real computer with a keyboard and a connection to a television screen, something you could actually use without being an electrical engineer yourself. Wozniak designed the Apple I in 1976, a single circuit board that you could hook up to a keyboard and a TV. It was elegant and clever, and his friend Steve Jobs saw something in it that Wozniak, who was more interested in the engineering than the business, might have missed. Jobs saw a product. He saw a company. The two Steves, Wozniak the engineer, Jobs the visionary, founded Apple Computer in Jobs' parents' garage on April 1st, 1976. They sold the Apple I for $666.66 because Wozniak liked repeating digits. But the machine that really changed everything was the Apple II, released in 1977. And here's where you can see how all these threads come together: Moore's law driving down chip costs, the counterculture's dream of personal empowerment through technology, the hobbyist community's passion, and Wozniak's extraordinary engineering talent. The Apple II had color graphics, sound, expansion slots, so you could add new capabilities, and it came in a sleek plastic case designed to look friendly and approachable, not like a piece of lab equipment. It was the first personal computer that felt like a consumer product, something you could put on your desk next to your lamp and your coffee mug and not feel like you were running a small data center. And then, in 1979, something happened that transformed the Apple II from a hobbyist's toy into a serious business tool. A Harvard Business School student named Dan Bricklin, together with programmer Bob Frankston, created VisiCalc, the first electronic spreadsheet. Before VisiCalc, if you were a business manager working with financial projections, you did everything on paper, with a calculator, on enormous ruled sheets called spreadsheets. If you changed one number, you had to recalculate everything by hand. VisiCalc automated all of that. You could change one number and watch every related calculation update instantly. It was, for the business world, a revelation, and it only ran on the Apple II. Suddenly, companies were buying Apple IIs not because they were cool gadgets, but because they needed VisiCalc. The killer app, as people would later call it. The application so essential that it justified the purchase of the entire machine. By the end of the 1970s, the personal computer industry was real. Apple was growing fast. A company called Commodore had the PET. Tandy had the TRS-80, sold through Radio Shack stores. There were dozens of smaller companies making their own machines, and the whole ecosystem was chaotic and exciting, and nobody was quite sure where it was all heading. But one very large company was watching from the sidelines, and in the summer of 1980, its executives made a decision that would reshape the entire industry in ways nobody, not even they, could have predicted. IBM, the colossus of corporate computing, the company that had dominated mainframes for decades, decided it was time to build a personal computer of its own. And the way they chose to do it, the shortcuts they took, the compromises they made, the deals they struck, created a set of consequences that are still playing out today. IBM's decision to enter the personal computer market wasn't born from excitement or vision. It was born from fear. The company's executives looked at Apple's surging sales, looked at the way small computers were starting to creep into corporate offices, sometimes bought by individual departments without even telling the IT department. And they realized that if they didn't act, they might lose control of the next era of computing entirely. And for IBM, losing control was unthinkable. But here's the thing about IBM in 1980. The company was enormous, bureaucratic, and slow. Building a new product the normal IBM way, through years of internal development, proprietary components, exhaustive testing, would take far too long. By the time a machine emerged from that process, the market might have already been won by Apple or Commodore or somebody they hadn't even heard of yet. So IBM did something completely out of character. They set up a small, semi-autonomous team in Boca Raton, Florida, led by an engineer named Don Estridge, and they gave that team extraordinary freedom. The directive was simple: build a personal computer, build it fast, and get it to market within a year. To do that, the team made a decision that seemed perfectly reasonable at the time, but turned out to be one of the most consequential choices in the history of technology. Instead of designing custom proprietary hardware the way IBM normally did, they built the machine almost entirely from off-the-shelf components. The processor was Intel's 8088, a variant of that 8086 chip we talked about, the descendant of the 808. Oh, that had powered the Altair. The disk drives, the memory chips, the keyboard, all sourced from outside suppliers. And critically, the architecture was open. IBM published the technical specifications so that other companies could build add-on cards and peripherals. This was deliberate. They wanted a rich ecosystem of accessories to spring up quickly, because that would make the machine more useful, which would drive more sales. Now, the other crucial decision involved software. The machine needed an operating system, the foundational software that manages the hardware and lets application programs run. IBM approached a small company in Seattle called Microsoft. Bill Gates and Paul Allen's little firm had grown since those Altair basic days, but it was still modest. And here's where the story gets almost absurdly consequential. IBM originally wanted to license an existing operating system called CP/M, made by a company called Digital Research, run by a programmer named Gary Kildall. CP/M was the dominant operating system for microcomputers at the time, but the meeting between IBM and Digital Research went badly. The exact details are debated. Some say Kildall wasn't there when IBM's representatives arrived. Some say his wife and business partner Dorothy refused to sign IBM's non-disclosure agreement. Some say it was a combination of miscommunications and bad timing. Whatever happened, the deal fell through, at least initially. So IBM turned back to Microsoft and essentially asked, "Can you provide us an operating system?" Gates said yes, even though Microsoft didn't actually have one. What Gates did was broker a deal to acquire a quick and dirty operating system called QDOS, literally, Quick and Dirty Operating System, from a nearby Seattle company called Seattle Computer Products. A programmer there named Tim Patterson had written it as a rough clone of CP/M, designed to work with Intel's 8086 processor. Microsoft bought the rights for about $50,000, adapted it, and licensed it to IBM as PC-DOS. And here's the kicker, the part that changed everything. Microsoft retained the right to license the same operating system to other companies. IBM agreed to this. They didn't demand exclusivity. From IBM's perspective, it probably seemed like a minor detail. They were IBM. Who was going to compete with them in personal computers? The brand alone would crush any rivals. The IBM PC launched on August 12, 1981, and it was an immediate success. Not because it was technically superior. In many ways, the Apple II and other machines were more elegant. But it had 3 letters on the front that mattered enormously. IBM. Corporate purchasing departments that had been nervous about buying computers from scrappy little companies like Apple suddenly felt comfortable. There was a saying at the time, nobody ever got fired for buying IBM. The PC became the standard for business computing almost overnight. But remember that open architecture? Remember that Microsoft kept the right to sell the operating system to others? Those 2 facts combined to create something IBM never intended, the clone market. Because IBM had used off-the-shelf parts and published its technical specs, other companies realized they could build machines that were functionally identical to the IBM PC. The only tricky part was the BIOS, the basic input-output system, a small piece of firmware that handled the lowest level communication between the operating system and the hardware. IBM had written its own BIOS, and that was copyrighted. But in 1982, a company called Compaq founded by Rod Canyon and two other Texas Instruments engineers, figured out how to legally reverse engineer the IBM BIOS through a cleanroom process. They had one team document exactly what IBM's BIOS did, every function, every input, every output, without looking at the actual code. Then a completely separate team of programmers who had never seen IBM's code wrote new code from scratch that did exactly the same things. This was legal, and it worked. Compaq released its first IBM-compatible PC in 1983, and suddenly the floodgates opened. Dozens, then hundreds of companies started building IBM-compatible machines. They could all run the same software, because they all used the same Intel processors and the same Microsoft operating system, which Microsoft was now selling under the name MS-DOS. Think about what happened here. IBM had created a standard, but they didn't own the two most critical parts of that standard. Intel owned the processor architecture. Microsoft owned the operating system. IBM owned the brand. And a brand, it turns out, is not enough to maintain control of an industry. Through the mid-1980s, the clone makers kept coming. They competed on price, driving costs down relentlessly. They competed on features, sometimes offering better machines than IBM itself. And all of them needed two things: Intel chips and Microsoft DOS. This is how Intel and Microsoft became the twin pillars of the personal computer industry, a duopoly that would dominate for decades. The phrase Wintel, Windows plus Intel, became shorthand for the entire PC ecosystem. IBM, the company that started it all, gradually lost its grip. They tried to reassert control in 1987 with a new architecture called microchannel, which was proprietary and required licensing fees. The clone makers responded by banding together to create their own standard. IBM's personal computer division never recovered its dominance, and eventually, in 2005, IBM sold its PC business entirely to a Chinese company called Lenovo. The company that had defined corporate computing for a generation walked away from personal computers altogether. Meanwhile, Microsoft was becoming one of the most powerful companies on Earth. MS-DOS gave way to Windows, which Gates and his team began developing in the early 1980s. The idea wasn't original. Graphical user interfaces, where you interact with the computer through windows and icons and a mouse pointer instead of typing commands, had been pioneered at Xerox PARC, the legendary research lab in Palo Alto. Xerox had built a machine called the Alto in 1973 that had all of this: windows, icons, a mouse, a what you see is what you get text editor. It was years ahead of its time. But Xerox, a company that made its money selling copiers, never figured out how to turn it into a successful product. In one of the most famous visits in tech history, Steve Jobs toured Xerox PARC in December 1979, saw the Alto's graphical interface, and immediately understood its potential. Apple's Lisa computer in 1983, and then the Macintosh in January 1984, brought graphical interfaces to commercial products. The Mac was beautiful, intuitive, and revolutionary. Its famous Super Bowl ad, directed by Ridley Scott, positioned it as the machine that would free humanity from the gray conformity of IBM. But the Mac was expensive, and Apple kept its architecture closed and proprietary, the opposite of IBM's approach. You couldn't build Mac clones. You couldn't mix and match components. This meant Apple controlled the experience, which made the product more polished, but it also meant Apple machines cost more and had a smaller market share. Microsoft, watching all of this, released Windows 1.0 in 1985. It was, honestly, not very good, Clunky, slow, limited. Windows 2.0 in 1987 was better, but still rough. The breakthrough came with Windows 3.0 in 1990, which was genuinely usable and ran on the vast installed base of IBM-compatible PCs. Suddenly, hundreds of millions of people had access to a graphical interface. It wasn't as elegant as the Macs, but it was everywhere. And in technology, ubiquity often beats elegance. By the early 1990s, the shape of modern personal computing was recognizable. You had Intel making faster and faster processors, the 286, the 386, the 486, then the Pentium in 1993. You had Microsoft providing the operating system that tied everything together. You had a vast ecosystem of hardware manufacturers competing to build the cheapest, fastest, most feature-rich PCs. And you had software developers writing applications for this platform because that's where the users were, which attracted more users, which attracted more developers. A virtuous cycle, a flywheel that just kept accelerating. But something else was happening in the background during these years, something that would ultimately matter even more than the PC itself. It started, like so many transformative technologies, with the military. Back in the late 1960s, the Advanced Research Projects Agency, ARPA, within the U.S. Department of Defense, had funded a project to connect computers at different research institutions so they could share data and communicate. The idea was partly practical and partly strategic. If you had a distributed network with no single central hub, it could survive partial destruction, which mattered quite a lot during the Cold War. The first message on this network, called ARPANET, was sent on October 29, 1969, from UCLA to the Stanford Research Institute. The team tried to type the word login. The system crashed after transmitting just 2 letters, low, which means the first message ever sent over what would become the internet was, accidentally, low, as in lo and behold. You couldn't make that up. Through the 1970s and 1980s, ARPANET grew and evolved. The key technical breakthrough was a set of communication protocols called TCP/IP, Transmission Control Protocol, and Internet Protocol, developed primarily by Vint Cerf and Bob Kahn. Think of TCP/IP as the common language that allowed completely different types of computers on completely different types of networks to talk to each other. Before TCP/IP, connecting 2 different networks was a nightmare of incompatible formats and standards. TCP/IP solved that by breaking data into small packets, routing each packet independently through the network, and reassembling them at the destination. It was elegant, robust, and scalable. On January 1, 1983, ARPANET officially switched to TCP/IP, and that date is sometimes called the birthday of the Internet, because it was the moment when the fundamental protocol that still runs the Internet today became the standard. But the Internet in the 1980s was still mostly a tool for academics and military researchers. Email was its killer app. Just as VisiCalc had been for the Apple II, email was the thing that made people want to be connected. Yet using the Internet required technical knowledge. There was no easy way to browse or discover information. You had to know where things were and how to access them. That changed because of a physicist working at CERN, the European Particle Physics Laboratory in Geneva, who had a problem that seemed mundane but turned out to be revolutionary. His name was Tim Berners-Lee, and his problem was simply this. CERN was a massive organization with thousands of researchers cycling through from universities all over the world, and they all used different computers, different operating systems, different document formats. Information was scattered everywhere, on different machines, in different databases, in people's heads, and there was no unified way to find it, link it together, or navigate from one piece of knowledge to another. Berners-Lee had actually been thinking about this since 1980, when he wrote a little program for himself called Inquire, named after a Victorian book called Inquire Within Upon Everything, that let him create links between related pieces of information. It was a personal tool, nothing more. But the idea stuck with him, and in March 1989, he submitted a proposal to his bosses at CERN titled Information Management, a Proposal. His supervisor's response, scribbled on the cover page, was famously lukewarm. Vague, but exciting, which might be the most consequential understatement in the history of technology. What Berners-Lee proposed, and then built over the next couple of years, was a system with three core components. First, a way of formatting documents so they could contain clickable links to other documents that became HTML, hypertext markup language. Second, a way of giving every document a unique address so you could find it that became the URL, Uniform Resource Locator. And third, a set of rules for how computers would request and deliver those documents to each other that became HTTP, Hypertext Transfer Protocol. Together, these three inventions constituted the World Wide Web. And here's what's important to understand. The web is not the internet. The internet is the underlying network. The cables, the routers, the TCP/IP protocols that move data around. The web is a system that runs on top of the internet, one of many applications that use it, just like email is another application. But the web became so dominant, so ubiquitous, that most people use the words interchangeably. And that's fine. It just helps to know the distinction. Berners-Lee built the first web browser and the first web server on a Next computer, one of those sleek black cubes that Steve Jobs designed during his years away from Apple. The first website went live in late 1990, and it was, fittingly, a page explaining what the World Wide Web was and how to use it. And then, Berners-Lee did something that shaped everything that followed. He gave it away. He didn't patent it. He didn't charge licensing fees. He convinced CERN to release the underlying code into the public domain in 1993, making the web free for anyone to use, build on, and extend. Think about what that means. If Berners-Lee had done what many people in his position might have done, locked it down, monetized it, controlled it, the web might have become a proprietary system, fragmented, expensive, slow to grow. Instead, it exploded. In 1993, a 22-year-old student at the University of Illinois named Mark Andreessen and his colleague Eric Bina created Mosaic, the first web browser that was easy to install, easy to use, and could display images alongside text. Before Mosaic, the web was text-only and clunky. Mosaic made it visual, intuitive, and, this is the key word, accessible to ordinary people. Andreessen went on to co-found Netscape, whose Navigator browser became the gateway to the web for millions of people in the mid-1990s. And suddenly, everything accelerated. The number of websites went from a few hundred in 1993 to over 100,000 by 1996 to millions by the end of the decade. The internet went from an academic curiosity to the central infrastructure of modern civilization in less than 10 years. That's breathtaking when you think about it. And this is where computing stops being a story about individual machines and becomes a story about connection. Because once billions of people are linked together, once information flows freely and instantly across the planet, the nature of computing itself changes. The computer on your desk, or in your pocket, is no longer a standalone tool. It's a window into a global network of knowledge, commerce, communication, and culture. The value isn't just in the processor or the memory or the software. It's in the connection. The late 1990s brought the dot-com boom, that wild period when it seemed like any company with a website and a dream could be worth billions. And many of them were, briefly. The bubble burst spectacularly in 2000 and 2001, wiping out trillions of dollars in market value. But here's the thing about that crash. The companies that died were mostly the ones built on hype rather than substance. The underlying technology didn't go away. The infrastructure that was built during the boom, the fiber optic cables, the data centers, the software platforms, all of that survived and became the foundation for what came next. Google, founded in 1998 by Larry Page and Sergey Brin in a garage in Menlo Park, survived the crash and became the dominant way people navigated the web. Amazon, founded by Jeff Bezos in 1994 as an online bookstore, nearly went under, but held on and eventually became, well, Amazon. The crash cleared away the froth and left behind the companies that actually worked. And then, in 2007, something happened that changed computing as profoundly as anything since the microprocessor. Steve Jobs, who by this point had returned to Apple after years in the wilderness, rescued the company from near bankruptcy and launched the iPod, walked onto a stage in San Francisco and introduced the iPhone. Now, smartphones existed before the iPhone. BlackBerry had been around for years, and various companies had been making devices that could browse the web and run basic applications. But the iPhone was different in the way that the Macintosh had been different from what came before it. It wasn't just a phone that could do computer things. It was a computer that happened to make phone calls. A full touchscreen, a real web browser, a device that felt intuitive in your hand. And when Apple opened the App Store in 2008, allowing third-party developers to create and sell software for the iPhone, it unleashed an entirely new ecosystem. Within a few years, there were hundreds of thousands of apps, and the smartphone became the primary computing device for most people on Earth. Think about that trajectory for a moment. From ENIAC, which filled an entire room and could be programmed only by physically rewiring its circuits, to a device in your pocket that's millions of times more powerful, connected to every other device on the planet, running software written by developers on every continent. That arc, from room-sized to pocket-sized, from isolated to connected, from specialized to universal. That's the story of computing in a single sweep. But there's another thread worth following as we wind down, and it's one that brings us right back to where this whole story started. Remember Alan Turing and his universal machine? That theoretical idea that a single machine could simulate any other machine, given the right instructions? Turing also asked a question that seemed almost playful at the time, but turned out to be one of the deepest questions in all of computer science. Can machines think? In 1950, he published a paper proposing what he called the imitation game, now known as the Turing test, where a human judge converses with both a human and a machine through text. And if the judge can't reliably tell which is which, the machine is said to exhibit intelligent behavior. For decades, that remained a thought experiment more than a practical goal. Artificial intelligence research went through cycles of enormous hype, followed by crushing disappointment. Periods researchers ruefully called AI winters, where funding dried up because the technology couldn't deliver on its promises. But something shifted in the 2000s. The combination of vastly more powerful processors, especially GPUs, graphics processing units, which turned out to be extraordinarily good at the kind of parallel mathematical operations that AI requires, along with enormous datasets from the internet and breakthroughs in a technique called deep learning, suddenly made things possible that had seemed decades away. Deep learning is built on neural networks, which are computing systems loosely inspired by the structure of biological brains. The idea had been around since the 1940s, but it took until the 2010s for the hardware and the data to catch up to the theory. In 2012, a neural network called AlexNet, developed by Alex Krzyzewski and his colleagues at the University of Toronto, dramatically outperformed traditional methods in an image recognition competition, and that result sent shockwaves through the field. Suddenly, machines could recognize faces, translate languages, transcribe speech, and generate text with startling fluency. And now, as you're lying here listening to this, we're living through the next wave of that revolution. Large language models, the technology behind systems that can carry on conversations, write essays, analyze documents, generate code. These are direct descendants of Turing's original question. They don't think the way you and I think. They're pattern-matching engines of extraordinary sophistication, trained on vast oceans of text, learning the statistical relationships between words and concepts. Whether that constitutes thinking is a question that philosophers and scientists are still debating, and honestly, it's a question that Turing himself would probably find fascinating. He'd probably also find it amusing that his imitation game, his playful thought experiment from 1950, turned out to be so prescient. So here we are. From pebbles and grooves on a counting board to neural networks running on chips with billions of transistors. From Charles Babbage's brass gears to Tim Berners-Lee's web to the phone on your nightstand. And what strikes me most, when you look at this whole story laid out end to end, is how human it all is. Every breakthrough came from a person, usually a stubborn, slightly obsessive person, who looked at the world and thought, there has to be a better way to do this. Ada Lovelace saw poetry in an unbuilt machine. Turing imagined a device that could think before anyone knew how to build one. Claude Shannon realized that electrical switches could do logic. Kilby and Noyce, working independently, had the same insight about putting everything on one chip. Berners-Lee gave away the most valuable invention of the decade because he believed information should be free. None of it was inevitable. At every step, things could have gone differently. Different decisions, different funding, different personalities, and the world you live in would look completely different. That's what makes this story so compelling. Even now, even as your eyes are getting heavy and the details are starting to blur together into something warm and comfortable. The story of computing is the story of people solving problems, one clever idea at a time, each idea building on the last, stretching back thousands of years to someone who first thought to slide a bead along a wire to keep track of a number. And the beautiful thing is, the story isn't over. It's still being written, right now, by people in labs and garages and dorm rooms all over the world. People who are looking at the tools we have today, the same way Babbage looked at his difference engine. Not as an ending, but as a beginning. Something to build on. Something to make better. And that's a good thought to drift off with, isn't it? That quiet, steady hum of human ingenuity, stretching back through the centuries and forward into whatever comes next, carrying us along like a current. You don't have to hold on to any of it. Just let it settle around you, all those names and dates and ideas, and let them blur into something soft and warm, like the glow of a screen in a dark room, like the hum of a machine doing exactly what it was built to do, quietly, reliably, while you rest